welcome to ECE 442. I'm glad all are safe and healthy. Let's continue our discussion from last time. Today we are going to wrap up the material on combinational logic, and we will get into what? Sequential logic. Clear? Difference between combinational logic and sequential logic is that in combinational logic, the output only depends on the what? On the input at the present time. The output at the present time depends on the value of the input at that time. There is no feedback. Whereas in sequential logic, there is feedback. Clear? There is feedback, which means what? The output at the present depends on the input and past values of the what? Of the output. There is feedback. That's called sequential logic. But we need to wrap up, first of all, the material on combinational logic. Last time I introduced you to yet another type of digital logic technology, which is dynamic logic. And very quickly, let's review it. What is dynamic logic? Dynamic logic, the logical level, is taken as a what? As the voltage stored across a what? A capacitor, rather than what? Rather than having a path to VDD or a path to the what? To the ground. Clear? The beauty of the dynamic logic is what? Is that you only need to implement the logic using the what? The PDM. Clear? So the dynamic logic, what do we have? We have a PMOS, only one PMOS, which is called the what? The free charge. PMOS. Yes. And then what? And then we do have the what? The logic function. And this is all what? NMOS. Yes, all NMOSes. These are the input to the logic. Let's assume it has 3 input, A, B, and C. And then we do have one more, which is the tail NMOS. This is called the tail, or they call it what? The evaluation NMOS. You understand why they call it tail? You understand why they call it tail? It's at the end. Clear? The output is taken from here. There is a capacitor here, every node, and ABC here, and so on. So on. This is VDD. And what is this? This is a clock. The book also again uses V for a clock, or you can write what? You can write a clock, and same clock for this one. Did you get it? Yes. By the way, what does that mean? When you see the same clock for this one and this one, what does it mean? It means they both cannot what? Cannot be on at the same time. Did you get it or not? Yep. They cannot be on at the same time because their input is what? Is the same. Clear? So if the clock is 0, this one is on, this one is off. If the clock is 1, this one is on, this one is off. Clear? Okay, let's review the steps very quickly. Step 1 is called what? The pre-charge phase. What do you put? You put P equal to what? 0. Yes, let's call this. Did I give it a name last time? M or Q or something, or no? I did not? Okay. Let's call this one MP, P for pre-charge, and this one is ME. ME is for evaluation. MP is what? Is on. ME is what? Off. Capacitor what? Charges to what? VDD. Does it reach the maximum? Yep. Or does it stops at some time? Or does it reach the maximum? It reach the maximum. VOH equal to what? VDD. Why? Because the PMOS passes a strong what? 1. Where is that strong 1 in the diagram? Can you show it to me? When I say passes strong 1, where is that 1? Where is that one? This is the VDD. Did you get it or not? That's the VDD. This one is what? This one is what? Low. Transistor is on. Yes. The value here is 1. It will what? Capacitor will charge to 1. Clear? No response. Clear?
Yes.
Oh, who is the source, by the way? For the PMOS, who is the source?
The VDD.
Be very good, VDD. Why? The PMOS, the source has to be the what? The highest voltage among all terminals, which is this. Yes? For the NMOS, who is the source? The ground. The NMOS, the source has to be what? The least of the voltages. Did you get it? Yep. This one is a logic, just general logic. So let's take an example. Suppose you want to implement A or what? BC. Did you get it? Yes or no? Yes. Oh, so let's sketch the truth table. A, B, C, X, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1. Clear? Okay. Yeah, 0, this one is what? 0. Yes?
0, 0,
0,
0,
0,
1,
1,
0. It's 1,
1, 1, 1, 1. Did you get it? Okay. By the way, if you sketch the K map to see if that function can be reduced, this is A, this is A bar, B bar, C bar, B bar, C, B, C, B, C bar. Okay, what do I have? 0, 1, 1. This is this one. And then what? These are all these. Yes? Yes?
Yes.
Okay. What is this?
A,
A. And what is this?
B, C,
BC. What does that tell you? You cannot what? You cannot simplify this logic. Clear? Okay. How do you implement the logic using NMOS? Only NMOS. Remember, NMOS is active what? Active? High. Did you follow me or not? So what do I do? I'm still waiting. So X is equal to what? Yes? What do I need? Yes or no? Which is what? Agree? Okay, one more time. Complement of A bar, this becomes AND. Bar BC is what? B bar or C. Did you get it?
Yes.
So what is it? No. Yes? And what is this? This is ME. This is the clock. Yeah.
Isn't that top MOSFET supposed
Huh?
to be?
Wrong answer?
The top MOSFET's A.
Oh.
No, that's
No, no.
that's part of the logic.
That top MOSFET is A. It's not the MP. Sorry.
That top transistor.
Oh, that part of the law. Oh my God. Jeez. Yes?
Yes.
And what is this?
A bar,
A bar? This one?
B bar, C
C.
bar.
Clear? So how many total transistors? 1, 2, 3, 4, 5,
6, 7,
6, 7,
8, 9,
8, 9,
11.
11 transistors. Did you get it? What if I'm using regular CMOS? Regular CMOS, which means what? Static CMOS, not dynamic. How much? Compare with yes? This portion is the same. Do you agree this one is the same? So what do I have? 1, 2, 3. Yes? In the PMOS, I will also have what? 3. So that's what? 6. Yes? And how many inverters?
3.
3 inverters. So how many?
12.
By the way, here you might tell me 11 transistor, 12 transistor, the saving is not what? It's not much. Do you agree? Yes. The saving will become better and better as the what? As the fan in increases. Fan in means what? The number of inputs to the logic. The higher the fan in, the saving for the dynamic logic is what? Is
Greater.
better. Did you get it or not? Oh, now keep in mind, I don't want you to ever think that the dynamic logic is replacing the what? The static logic. It's the other way around. The static logic is the one that is what? That is robust and the one that is used the most. Dynamic logic, as we'll see most of the time, you use it for what? Memory, DRAM, dynamic RAM, clear? Or somewhat specialized electronic circuits that require what? Less area. Did you get it or not? Yes? Okay, good. Now, let's see how does it work. Okay, what do I do? Step number 1, pre-charge, phase, let V equal to what? 0. Yes? Which means what? Capacitor will charge to what? To 1. Is the logic available?
No.
The logic is not available. Did you get it or not? Which means what? You cannot get that function. So logic is available only during the evaluation phase. Clear so fast? Now, in the evaluation phase, what will happen to the capacitor?
Discharge.
If the inputs to the logic is such that the output is a what?
0.
1. What does it mean? It means this one will hold on its 1. So I want you to say this. 1 is the x equal to 1. Did you get it or not?
Yes.
So any one of these input combination, this, which is equivalent to what? 2, 3, 4, 5, no. Yeah, 5, I'm sorry, 5. Yes? Any of these? No, I messed up. Not the 2. So what is it? 3, 4, 5, 6, 7. Yes? Any of these inputs. Let's take one of them. Let's take the 3. 0, 1, 1. Look at the logic. 0, 1, 1. This is A. Okay. What can you tell me about this? On. B, on.
On.
Sorry, B bar. This one is B bar. Is this B bar?
Yes.
Yeah, B bar.
It's off.
Off.
On.
Off. What does that mean?
No path.
no path to the ground, X will remain what?
One.
1. What are we hoping? We are hoping that what? That the capacitor will hold a charge. This is the capacitor. Did you get it?
Yes.
No response. Did you get it?
Yes.
Okay. Now here we have a problem. I will show you that in just a second. But let's look at these, which is what? 0, 1, 2. Yes? Let's take, for example, 1. A is 0 on. Yes? B is 0 on. C is what? 1, which is what? Off. But there will be what? There will be a path like this. Remember, this one is on during the evaluation, which means the capacitor will discharge to what? To 0. Did you get it or not?
Yes.
Okay. Now, last time I showed you during the evaluation, phase, the input to logic cannot change from 1 to 0. Clear? No response. Clear? It can change from where? It can. Or what? No change. Did you get it? Why? Why? Why it cannot be from 1 to 0?
Because the output can't go from.
Huh? Why it cannot be from 1 to 0?
You'll lose the logic.
And there is no way that I will what? I can bring this one to what? To BDD, except during which phase?
Pre-charge.
The pre-charge phase. Did you get it or not?
You cannot change from 1 to 0,
From 1?
or 0 to 1.
It's inverted.
Oh, I see.
No, it's inverted. 1 to 0. Yeah. Did you get it? No response. Did you get it? Okay. What was the solution to this problem?
Domino.
You're using Dominos logic. So solution. What is Dominos logic? What do?
Inverter.
I take this what? I take this X and I connect it to a what? A static what? Inverter. Yes? No response. Yes? This is X. No response. Do I have access to X? No, I have only access to what? To the output of the inverter, which is the X bar. Did you get it or not? No response. Did you get it or not? Okay, this whole thing is called what? Dominos logic here. Clear? Now, there is a couple of other problems that I need to show you. Okay, first of all, capacitor. Oh, did you understand so far? Yes or no? Okay. Voltage. Did I show you last time a diagram that shows you that transition from 1 to 0 is not allowed for the inverter? A diamond diagram. Yeah, this one. Yes, I did. Clear? Okay, good. Voltage on capacitor leaks. What does that mean?
If you don't.
So I what? I pre-charge the capacitor to what?
BDD.
To BDD. Yes. So the voltage across the capacitor is what? BDD. Yes. Does it remain BDD?
No.
What happened? What happened? It begins to what?
Draw.
leak. Did you get it? Not, by the way, that's not the reason. That's not what? That's not because what? Because the input is such that this one will what? Will discharge. I'm talking about what? The inputs is such that the output is still what? One. So for example, here, what is it? What is it? Let's take 1, 1, 1. Yes? 1, 1, 1. The output is supposed to remain what? 1. But in reality, it's not equal to what? 1, because the capacitor will what? Will leak. Clear? Do we have a solution for this? I already showed it to you earlier, but you forgot. Which is what? Which is the following. Remember, this one is 1. Yes? Yes? Okay. Let's see if you can help me understand this. Why this one does not look good? Yes. What is this? That's a PMOS. Do you remember what did we call it? Of course not. Restoration. PMOS. What is it restoring?
The 1.
Well, it's restoring a 1. Did you get it or not? Okay. Now, let's take the example just to make sure that you get the point clear. Let's assume that we are designing just an inverter. Just an inverter. Yes? What is X equal to?
A bar.
Yes or no? Okay. If X is equal to 1. Yes? If X is equal to 1, what is this one?
0.
0.
On.
On. PMOS passes a strong what?
1.
So even if this point begin to what? Leak? Yes? What will happen?
Stays 1.
This one will pull it to what? 1. Did you get it? No response. Did you get it?
Yes.
Here we have a dilemma. Let's see if you can help me with the dilemma. If X is equal to what? If X is equal to 0, what is this one?
1.
1, which means what? This one is off. But that's not a problem. Do you follow me or not? Because it means what? It means the capacitor has already what? Discharged to 0 through this NMOS. A is equal. When will this one be equal to 0? When will this one be equal to 0? If A is equal to what? 1. Did you get it or not?
Yes.
Okay. But if A is equal to what? 1. If A is equal to 1, yes? Which means this one is working. What is X? 0. We just did this one. One more. If A is what? 0. What is this? 1. But it's leaking. What is this one is doing? Restoring it. Yes? Yes? It's restoring it to what? To 1. If A is what? If A is 1, then this one doesn't matter. Why? Because if A is 1, what is this? 0. What is this? Which means the PMOS is what? It's off. Did you get it? This is called capacitor leakage. I almost said child leakage. Cannot believe I said that. Clear? Okay, good. Now, can we change it back to the original one? What was it? I lost. What was it?
I don't know. B and C.
What is this?
A bar. B bar or C bar.
clear? Okay, good. Did you understand this one? Okay, let me ask you a question. If one second. 0, 0, 0. A is 0. A is 0. B is 1. And C is 1. These are all off. Yes? But A is conducting. Do you agree that this one is conducting? This one. Do you agree that A is conducting?
Yes.
Okay. Now I am going to raise this and tell me what happens. Listen to me. There is a capacitor here. Yes? Call it C1. Yes? Now, at every node, there is a parasitic capacitor. Which means what? In here, there is a capacitor called what? C2. Yes? In here, there is a capacitor called what? C3, and so on and so forth. You follow me so far?
Yes.
Okay. Now, I want you to see this case. A equal to 0, B equal to 1, C equal to 0. Yes? Can you tell me if A1 is if this one is working?
Yes.
This case, here, put a circle. Yes? Can you tell me if A is working?
Yes.
This one, is it working?
No. Yes.
Huh?
Yes.
Yes?
Yes.
Okay. And this one is on. Yes? This one? No, I want when X is equal to 1, sorry. Not this case, I'm sorry.
Their case bar.
This case. I'm sorry. This case. Yes? What is A?
On.
On. This one is on. B is what? Off. C is off. Yes? What is the output supposed to be?
One.
Which is the what? Which is the pre-charge on the capacitor. Agree?
Yes.
Forget about the leakage for just a second. This is a different phenomenon. If this one is working, there is a what? There is a charge sharing between these two. Did you lose me?
No.
Which means what? As if you have this. Follow me. This is C1. This is what? C2. Did you get it or not?
Yes.
If this one is working, what will happen?
C2 will charge.
What will happen is that this switch will be what? Closed, and they will what? They will share the charge. Why they will share the charge? Because they are connected in what? Which means the voltage, what is the voltage across C1? What is the voltage initially?
VDD.
VDD. Did you follow me or not? The voltage across this one is not VDD, some other voltage. Did you get it or not?
Yes.
But if the switch closes, the voltage here and the voltage here has to be what?
Same.
The same. Why? Because they are in what? Parallel. Did you get it or not? How will it be the same? How will the voltage be the same? If there will be a what? Charge sharing. Did you get it? Can you give me an equation? Before the switch closes, what is the charge on C1? Oh God, heaven. What is the relationship between the capacitor, the charge, and the voltage? Charge on this is what? C1 VDD. Yes?
Yes.
Yes? What is this? What do you get by multiplying capacitor times the voltage? This is 240. You get the what? Charge on what? C1. Yes? After the switch is closed, what is the charge?
C1 V2.
C1 plus C2. Question, why am I adding? Well, they are in parallel, times what? Let's call it delta B. What is delta B? Delta B is a new what? A new voltage across them. Yes? Which means what? What is delta B? That's how much voltage on each capacitor will be. You lost me here. Did you lose me? Oh. One more time. One more time, please. What is the initial charge on C1?
VDD.
Before you apply the input. Before you apply the input. During the pre-charge. Yes? What is the charge on C1?
VDD.
It's C times what? VDD. It charged all the way to what? To VDD. Yes? But when the switch closes, which switch? Which switch?
The A.
Sorry, which NMOS is working?
A1.
This one. Did you get it or not? Notice, by the way, this one and this one are not working. Which means what? They are open. But is this one working?
Yes.
But that will not affect the what? The truth table. Will it? It will not affect the truth table. But there will be a path from here, here. And instead of going to the ground, it will go what? Here. Did you get it or not?
Yes.
Now, what does the total capacitor become? When the switch closes, what does the total capacitor become? C1 and plus C2. Yes? But the total voltage cannot be VDD. Why? Because it means what? It means that you created charge which wasn't there to begin with. Did you follow me or not?
Yes.
The charge wasn't there to begin with. How could you get what? C1. How do you get this? You started with the charge. Yes, how do you get more charge? Did you get it or not? So what happened? C1 plus C2, why am I adding? Capacitors in parallel, times a new voltage. This is the delta B, by the way, is it the same voltage across both of them?
Yes.
Why? Because they are in what? In parallel, it's the same voltage. Yes? That's the what? That's the C1 plus C2 delta B. The total charge is the same, nothing is lost. But what happened? Some of the charge that was on C1 is what? Shared with what? C2. Did the voltage across C1 goes down?
Yes.
Did the voltage across C1, which is VDD, does it go down?
Yes.
It went down. Not because of leakage, but it's because of what? Charge sharing. Did you get it or not?
Yes.
Yes.
Yes or no?
Yes.
I'll get your question in a minute. How do we solve? Is there a solution to this? Is there a solution to this? I tell you what? I tell you pre-charge all the nodes. Which means what? When you connected this to VDD, when you connect, in other words, follow me. Clock. That clock is the same as this clock. You follow me or not? And then what? Take it all the way to which node? This node. Yes? Yes? So what are you pre-charging? Both C1 and C2 to what? VDD. So when what? when this one is working, there will be no what?
Charge sharing.
Charge sharing. Why? Each one of them has what? VDD across it. You lost me here. Did you lose me? Each one of them will have what? VDD. There will be no charge sharing. Yeah.
If you don't pre-charge all the nodes, won't there be a VTN voltage difference between C1 and C2 because of the?
If you don't what? Pre-charge?
Yeah, will there be? There will be VTN voltage difference because the source is not ground anymore. It's the capacitor.
You mean this case?
Yeah, because the source of the A bar is going to be on the capacitor, not ground. So that there's going to be the voltage difference. No.
I didn't get it. You are pre-charging this node, not this node.
No, without pre-charge. If you don't pre-charge.
It's not a pre-charge, you have this case.
But because the source of the NMOS is not at ground, there's
Doesn't matter. What I'm trying to tell you is that if you are not going to pre-charge all the nodes, only this one, then C1 and C2 will have different voltages.
Okay.
This is what you are saying. They are different voltages. You agree?
Well, but I'm asking if because you said they'll charge share to the same voltage.
Okay. This is with you just told me do not pre-charge all the nodes.
Yes.
Didn't you just say that?
Yeah.
Which means what? Remove this. Remove this. Yes?
Yes.
What is the voltage across C1?
VDD.
VDD. The voltage across C2, is it VDD?
No.
No, some other values. I don't care which value it is, but it's some other value. Yes?
Yes.
Okay, when this one is on, the switch is what?
Closed.
Closed. Yes? What will be the new voltage across the capacitors? Delta V, which is equal to what? C1 over C1 plus C2 times what? VDD, which means what? It went lower. I'm not sure I understood your question. What is your question?
Because the source of A is not connected.
What are you trying to imply? The
Right.
voltage across C2 is, you are telling me the voltage across C2 is not the same as the voltage across C1. Is this?
Will it not stop VTN lower than C1 when C1 drops and then this one?
Please have mercy on me.
It's
Let's not worry about the value.
okay.
Are you telling me, this is what you are telling me. You are telling me the voltage across C1 and the voltage across C2 is what? It's not the same because the NMOS does not pass a strong what?
Strong one.
A strong one. Is this what you are telling me?
Yes.
I agree.
Okay.
All what I'm saying is that B1 and B2 are not the same.
Okay.
But when the switch closes, the voltage has to be what? The same because they are in parallel.
Okay.
Yes? What happened?
The
What
C1
happened?
drops.
Part of the charge here is shared with this one. Until what? Until the voltage is the same between each one of them.
Okay.
Did you get it or not? I got your point. You are telling me the NMOS passes a what?
Weak one.
A weak one. So if this one is 1, this one is not going to be what? 1, because the NMOS passes a what? A weak 1. Agree?
Yeah.
I agree.
Okay.
I agree.
That was all.
What I'm saying is that it will be different what?
Full.
Different voltages across C1 and C2.
Okay.
But eventually, they will be what?
Same.
They will be the same voltage. Why? Because this NMOS is on, which means what? The switch is closed. You follow me or not?
Yes.
So who is going to lose voltage?
The C1.
C1 is going to lose voltage. Clear?
Yes.
That is how much it will become. Did you get it or not?
Yes.
No response. Did you get it or not?
Yes.
Okay. Now, again, you can see there is a lot of problem here. Do you agree there is a lot of problem?
Yeah.
In other words, if you see all the problems, you might end up with a conclusion, it's not worth it.
Yeah.
Did you follow me or not? Most corporations, especially Intel and the chip designers, reach that conclusion. They said what? Dynamic logic has a lot of problem, does not justify the what? Does not justify replacing the static logic with dynamic logic. We prefer to stay in what? Static logic. This one, I just introduced it to you because in RAMs, there is a special type of RAMs, which is called what? DRAM. Which is dynamic random access memory. This type of memory requires what? Huge amount of transistors, like in billions with a B. Clear? So they try to save as much what? As area as possible. They use what? Dynamic logic in this. Did you get it?
Yes.
Did you understand it?
Yes.
I don't want to dwell on this one, but did you get the idea? Because it has too many problems.
Yeah.
Clear? Okay, good. Now, let's move on. By the way, before we go to sequential logic, I want to introduce you to yet another class. And tell me what is the problem with this one. Pseudo-NMOS. Pseudo-NMOS logic. No clocks in here. No clocks in here. So, let's assume pseudo-NMOS logic for an inverter. This is A. Yes? This is the NMOS. Yes? Okay. For static logic, what should it be? A. Do you agree? No response. Do you agree? Okay. So the NMOS tells you what? Remove this one and connect this one to the ground. No response. A, X.
When A is 0, X is 1.
If A is 0, what can you tell me?
Off.
Off,
On.
on, output,
1.
1. So far, so good?
I am confused, I won't lie.
Could you repeat that again?
I'm confused. How did that become a 1?
A is 0. Does it
Yeah.
work?
No.
Open. This one is always working. Do you agree that this one is always working?
Yes, but it looks like it would pass a 0? Because it's connected to ground, or am I
No,
not
no.
understanding?
Oh, sorry. Oh my God. I know why you are confused. It's BDD. Now I see why you were confused. Now make sense?
Yes.
Yeah.
Okay, good. One more time. By the way, this one also was used in some application, but it has one major problem. I want you to understand it before we go to the sequential logic. One more time. If A is 0, working or not working? Not working. Working or not working? By the way, is it always working?
Yes.
It's always working. Agree? Okay, which mode, by the way? Which mode? Look, this is the source. VDD. The gate is what? 0. Which mode? Always saturation mode. This one is always in saturation mode. Did you get it or not? Okay, good. Let's not worry about that right now. A0, 1. Yes?
Weak 0.
I want you to tell me what is going to happen. What is going to happen? Is this one on?
Yes.
Is this one on?
Yes.
This one is always on. What will happen?
It's a weak 1.
Tug of war. You follow me or not? This one is trying to push it where? Up to 0, up to VDD. This one is trying to push it where? Down to ground. Yes? Who should win?
Bigger one.
You should, this one should what? In other words, both transistors are working, but help me, the NMOS should win. What does that mean?
NMOS needs to be bigger.
Huh?
It needs to be bigger.
The sizes. This is said to be ratioed. I want to introduce you to this. Ratioed logic as opposed to ratioless logic. I want you to understand the difference between the two before I show you equations. Go to back to the static. Agree? Okay. Help me. Can they work together? Can both transistors be conducting at the same time? No. Either one is on, the other off, or vice versa. Agree? What does that tell you? It tells you your choice of W over L N, W over L P, your choices for what? For the aspect ratio, this is called the aspect ratio, which is W over L, matters for the performance, not for the operation of the logic. Did you understand the difference between operations of the logic and performance?
Yeah.
Performance means what? I don't care how you choose this ratio, the logic will still what? Work no matter what. How you choose the ratios. Did you get it or not? Yes or no? What will matter? It matters the performance. For example, in terms of the speed, propagation delay. Did you get it or not? But not because of the what? Of the operation of the logic. Did you get it or not?
Yes.
This is what is referred to as ratioless. Clear? Which means what? The ratio of W over L is not important as far what? As far as operation of logic is concerned. Did you get it or not? It affects what? You did not get this one. Did you get this one? Yes or no? Can I choose what did we call this, by the way? N? Where is it, this one? N, P. Yes? Can I choose N equal to P?
Yeah.
Well, the logic works,
Yeah.
but the performance might not be top notch. Did you get it or not?
Yeah.
But that the logic works.
Yeah.
The logic works. This is called ratioless. It does not what? The W over L is not important as far as the what? Operation of the logic is concerned. It what? It is for performance only. Did you get it? In Pseudo-NMOS. But wait, what are we gaining over the static? How many transistors are we using here? 2. How many transistors are you using here? 2. Now I want you to think about the following. Suppose the logic is this. whatever. How many inputs? Huh? A lot. Which is what? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes? If I want to implement in a static logic, how many transistors do I need? Forget about inverters. Forget about the inverter as input. Let's assume all of them are what? Non-inverted. Yes? How many transistors do I need? 18. Everybody understood why it is 18? Because I need 9 for the what? For the PDN and 9 for the what? 1. In Pseudo-NMOS, how many do I need? 10. Did you understand why 10? Because this is always what? 1 PMOS with a what? With the gate grounded. The logic is implemented where? In the NMOS. In the PDN. Did you get it or not? And there is no evaluation or pre-charge or so on and so forth. In other words, it's not dynamic logic. Did we save from 18 to what? 10. Did we save?
Yes.
We saved a lot. As the fan in becomes bigger, the saving becomes what? Higher. Did you get it? But this one is a ratioed logic. What does ratioed logic mean? Your choice of W over L is crucial for the operation of the logic. Not for the what? Performance. But for the logic to work. Why? One more time. If A is 1, is this one working? This one is trying to pull this one where? Down. Is this one working? This one always working. You follow me or not? What is it trying to do? Pull it up. Clear? Who should win? The NMOS should win. Did you follow me or not? Yes or no? The NMOS should win. But we need to what? Make sure that the choices of W over L, by the way, is it the same current? The DC current, the DC, not the AC. DC current, is it the same?
Yes.
Why? They are in series. Did you get it or not? Yes or no? But the choice of W over L matter. Who should win? One more time. The NMOS should win over the what? Over the PMOS. Clear? And here, both transistors are working. But NMOS should what? Should win the race. It should win the win. Should win the race. Clear? Which one should have the larger W over L? Remember, by the way. What did you say?
NMOS.
Correct. Why?
Because otherwise it will float in the middle.
That's not the answer that I was looking at. Remember, the resistor is inversely proportional to what? To W over what? L. Did you get it or not? Yes or no? You forgot it? R on. Is 1 over what? Kn, VDD, sorry, VGS. Yes?
Yes.
Do you see what W over L is? Where? In the numerator or denominator? Which means what? I want to make W over L what? Large. So that the resistor become what? Smaller. Which means what? It means this one prefer to what?
Down.
Discharge rather than what? Charge. Why? The current always chooses the what? The path with the least what? Resistance. Did you lose me? Did you lose me? Everybody? Now, but we do have another problem. Is there a static power dissipation?
Yes.
There is static power dissipation. Yes? Not in this case do we have a static power dissipation. No, we don't have a static power dissipation. But in here, do we have a static power dissipation?
Yes.
Why? Both of them are what? Are working. Did you get it or not?
Yes.
Question, someone. Yeah.
So the bigger the NMOS, the lower the VOL.
That is correct. By the way, the VOL is not going to reach 0. You follow me or not? Because this one is trying again to pull it a little bit up. This one is trying to pull down. It does not reach 0. which means what? That's another what?
Downside.
Another disadvantage, another not so good. Because you would like what? You would like the voltage to swing, to have the full swing. 0 to what? VDD. The VOL is not equal to 0. A little bit higher. Clear? No response. And also, the major thing is the what? Is the power, static power. We are not talking about dynamic power. We are talking about what? Static power, which means what? The inverter is not switching. The inverter is not switching. You don't understand what dynamic power and static power mean?
Mm-hmm.
Static power means what? The inverter is not switching. It's at a what? Stable state. Did you get it? Dynamic is when it is switching from 0 to 1, 1 to 0. This one has a static power dissipation, which means what? Even if the inverter is not what? It's not switching, there is what? Static power dissipation. So what is the advantage? I'm still waiting. The area is from what? 18 to what? 10 in our example, this example. 18 to 10. That's the only advantage. After a while, they said, what? It's not worth it. Did you get it or not? They come up with different technologies every day and now. They say, what? Is it worth it? Everything has a pros and what? Cons. If it is not worth it, but I just thought to introduce you because I wanted to introduce you to these two concepts. Did you understand what is the difference between ratioed logic and ratioless? Mm-hmm. Ratioed logic, the choice of W over L matters as far as the what? As the operation of the what? Of the logic is concerned. Clear? Ratioless means what? Whatever W over L you choose, the logic will still what? Will still work. But the performance might be what? Might be higher, lower, whatever. But the logic is still work. It's still as an inverter. Yes.
So this is basically the same as the resistively loaded.
This one is resistively, what do you mean basically? It is resistively loaded. This one is acting as a what? As a resistor. Did you get it?
Yes.
No response. Did you? Yeah.
So just to make sure I'm understanding correctly, ratioed logic means like if we chose W over L in a poor sense, then that wouldn't act as an inverter per se?
That is correct. In other words, if you chose, just an example, if you chose W over L for this one, higher than this one, the logic is not going to work. It's not because what A is 1, what would this one be?
1.
1. Is that an inverter?
No.
Then logic did not work.
Okay.
Did you get it? The logic did not work. In the case of ratioless, I don't care how you choose the W over L. The logic will still what? Work. You follow me or not? But the performance might what? The TP, does TP, by the way, depend on W over L? You just have it in the exam. Yes? TP is propagation delay. It's a function of inverse propagation to W over L. Yes or no? Yes. So the TP might be different, but the logic will still work. Clear? No response. Clear?
Yes.
Okay, good. This is called the pseudo-NMOS. What does pseudo mean? The word pseudo. Huh?
Sort of, kind of.
Okay. Pseudo means what?
Like kinda, sort of.
Kind of, sort of, yeah, sort of NMOS. Because everything is implemented in what? In NMOS, except for what? One transistor only, which is which one? This one. All the others, all the logic is NMOS. And there is no need for what? Clock, pre-charge, clock, and so on and so forth. It's not dynamic logic. This is static logic. Did you get it or not? Yeah, but it suffers from the problem that in some situation you are going to have what? You are going, because this one is always on. Do we agree this one is always on? This one is always on. This one is what? What is this in which mode?
Saturation.
Huh?
Saturation.
Why? The VG, what is the S? This is PMOS. Yes? What is for the, what is S? What is V, G, S? What is V, G, S, P? No response.
I would say VDD.
Look at the circuit. What is the G?
Zero.
What is the S? So what is VGSP? Yes? Where are we? Did you forget the characteristic of the PMOS?
No.
What does it look like? Let's see. Oh my God. Jeez. Yes? In the PMOS, everything is negative. Which means what? The current is negative, VDSP is negative. You follow me or not? And V what? VGSP is also what? Negative. And the threshold is also what? Negative. So what do we have? Did you get it or not? Now, as you go here, as you go this way, the VGS becomes more negative. As you go this way, the VGS becomes more what? Negative. But that's the ultimate. It cannot go what? Less than minus VDD. Did you get it or not? So where are we? We are on this curve. But the question is what? Are we on this? Which is what? The ohmic region or the triode region? Or are we in the what? Saturation region. Yes? Yes? What is the condition? What separates the saturation from triode to saturation? Okay, let's remind you of the NMOS first of all. Okay, for the triode, what is the condition? VGS has to be greater than what? VT. Yes? VTN. And this one is positive. In NMOS, everything is positive. Yes? And what is the other one? VDS has to be what? Less than what? Did you get it or not? Which means what? It means the channel is not pinched. Remember the channel, the N channel is not pinched. Clear? Okay. For saturation.
Greater than
What is the VDS? Clear? That's for the NMOS. For the PMOS. Same thing, but it's now what? Absolute values. So for PMOS,
Absolute value.
what does that mean? If you remove the absolute value, what was it before? It was what? Agree? No response. Yes or no? This is negative. This is negative. Yes? If you multiply both sides by negative, what will happen to this one? Flips. And now you put absolute value. Did you get it?
Yes.
Oh, how about this one?
Absolute value.
Same thing. Absolute value of VDS is what? Yes? This one. And PMOS, all of these voltages are negative. You follow me or not? So when it is negative, see this one, it tells you this one needs to be more negative than this one. Yes? So for example, just for sake of argument, if this one is minus 1, this one should be what? Minus 2. Yes? When you take when you multiply, another one, minus 2 is less than minus 1. Do we agree?
Yes.
If multiply both sides by 1, what would you get? Sorry, by minus 1, what would you get? You would get 2. Did you get it or not? Why? Why did this one flip? Because you multiply both sides by what? -1. Yes? So all the equations are the same. Just use what? Absolute value. Clear? Now, let's see if this one applies. What are we talking about? Absolute value of BGS. What is the absolute value of BGS?
BDD.
BDD. Yes? Absolute value, some number, small number. Let's say what, 0.5 or whatever. Absolute value of what? VDS, which is this voltage. Yes? Now, remember this one, if this one is off, if this one is off, yes? This one is on, what is this voltage is? Huh? Which means what? What is the voltage difference between this one and this one? Zero. Which means what? Where, which one does it apply? Remember, absolute value of BGS is how much? You lost me. Did you lose me?
I'm just trying to think about the
Yeah.
math.
All right, you lost me. I can see your face, it looks weird. You are weird anyway, but it becomes weird. Can we concentrate? I want you to look at the case one. This one is 1. Yes? Which means what? What does it tell you? A is what? A is off. Yes? So this one is 1. Does this one charge all the way to BDD? Why? Because the PMOS passes a strong what? Strong 1. Now, what is VDS? This VDS. Sorry, B is the voltage between this one and this one. How much is it? 0. Which means what? 0. Yes? What is VGS? GS minus what? BDD. Absolute value? BDD. Yes? Minus what? Small value, BT. Agree? Which means what? This one is always what? Huh? Triode. This one is always what? Clear? That is why when you said a moment ago, this is similar to a what? A resistive loading inverter. The PMOS is acting as a what? As a resistor, because it's acting in a what? In a triode mode. Lost me? Yeah.
Will it go
By the
into-
way, the NMOS is acting as a what? This is in a triode mode. The NMOS is acting as a what? When the input is high. Saturation mode. Yes or no? Which current is higher? The saturation or the triode? Saturation. Which means what? I want this one to what? To win the race. Yes or no? No response. Yes or no? By proper choices of the W over L, we need to make sure that this one wins the race.
When the A goes to 1 and the output output voltage drops, doesn't the PMOS saturate when the VGS for the PMOS increases?
When this one is what?
On, and the output voltage drops, the VGS on the PMOS increases.
No, but initially, what it is,
Oh.
before it's not going to drop instantaneously. It's going to take its time. So this one will start as a what? As a triode. Clear? No response. Clear? You lost me here. But anyway, I'm not going to ask you a question on this. But did you understand this?
Yes.
This is more important than this. Did you understand the difference between ratio to logic and ratio to logic?
Yes.
Okay, good. Yeah, next. Let me introduce, I thought I will be able to start today. I did the work. Okay, sequential. Logic. What is the basic unit of a sequential logic? You want to design a sequence. First of all, can you give me examples of sequential logic? 320. 320. Did you take 320? When? With who? Huh? Urusta or Al-Naghi. Doesn't matter. Did you study sequential logic? Can you give me examples of sequential logic?
Ring counter.
Counters, shift registers, flip-flops? Yes? What is the basic element? What do we call the basic element? It's the latch. Clear? The latch. Is this the first time you hear the latch? What does the latch mean? English. I run out of time. I cannot start this. Are these the same words? A latch and a flip-flop. A flip-flop. Is it the same or it's not the same?
Not the same.
But people sometimes use it interchangeably because they are sloppy. You cannot be sloppy. What is it? First of all, what does latch mean? Hold. You are trying to hold on some value of the input. Clear? Store it. Clear? The latch is what? Level trigger. Level trigger, which means what? All what it needs is what? High level of the clock or what? Low level. It's level trigger. Whereas the flip-flop is what? Edge trigger. Did you get it or not?
Yes.
But I ran out of time because I need to return the exam for you. Next time we will get I'm going to return the exam. If you did not take solution, pick a copy. If you have taken solution, then that's fine. Okay. Result of the exam is very sad. Very sad. If you are going to do better in the second midterm, I will give more weight to the second midterm. Did you follow me or not? I can do whatever I want. I'm the teacher. Did you get it?
Yes.
But if you keep the same attitude, which is the following, I'm going to explain to you the attitude. I come to the class, I never miss a class, but I don't do anything throughout the week. I don't practice, I don't read the textbook, I don't do homework, whatever. Prepare to take the course again next semester. And unfortunately, it will be also me. You follow me or not? Not too many people like to teach this course. But in my opinion, it's a very important course. This, with digital technology, is very important. If you change your attitude, better possibility to surpass the class. If you keep your attitude, nothing will change. I don't believe in miracles. You believe in miracles, that's your business. I don't believe in miracles. Randy